Okay, let's take a look at a few more characteristics of matrices. And basically, for intuition, a matrix is actually a linear transformation operator in space. And this sounds very nice, linear algebra. In machine learning, we try to find a transformation that maps inputs to outputs, and here you see linear transformation operator in space. I'm going to prove it to you. So let's take a vector and a matrix. The vector is 1, 1. This is the matrix. Let's take the transpose of the vector. So this is one row times 2 columns. Okay? And then A. So let's do here 1, 1 times the matrix, and the matrix is 2 rows, 3 columns. Right? So we're fine because this 2 is equal to this 2. So the end result I already know is gonna be a 1 times 3 matrix. It's just gonna be like this. 1 row, 3 columns. So if we multiply, so let me just 1, 2, 3, 4, 5, 6. So we're going to calculate the number here is 1 plus 2 plus 3. Sorry, no. Is 1 times 1 is 1 plus 1 times 4 is 4. 1 plus 4 is 5. 1 times 2 is 2, 1 times 5 is 5, so 7. 1 times 3 is 3, plus 6 is 9. So it's fantastic, because you apply the matrix to a vector. Your vector was in 2-dimensional space, and suddenly you transform into a higher dimensional space. This becomes a 3-dimensional vector. Yeah? So you see, with matrix we can make transformations, and that's why matrices and blocks of numbers are so important in machine learning. Because that's basically what you're going to do. You're going to process blocks of numbers, massive blocks of numbers. Yeah. Okay, transpose of a matrix. We've seen the transpose of a vector, where a column vector becomes a row vector. Transpose of the matrix is exactly the same. Rows becomes columns. Yeah. So this will be 1, 2, 3, and this will be 4, 5, 6. Yeah? This is a transpose of A. Now, rank of a matrix. The rank of a matrix is the number of linear independent column vectors. As I mentioned, a matrix is a stack of column vectors. And the rank is the number of linearly independent. Yeah? For example, this matrix A is a 3 by 3 matrix. If all these columns are linearly independent, the rank of that matrix would be 3, and the matrix would be full rank. But if you look carefully, you see that the third column is just the addition of the 2 previous columns. So that means that the rank here, the rank is 2. Yeah? Why is that? Well, you have 2 vectors in 2-dimensional space. You have one vector, the second vector. And the third vector is not a third dimension sticking out of the board. It's just the sum of the first 2 vectors. Yeah? So you remain in 2-dimensional space. Yeah. Okay. Now let's take a look at the determinant of a matrix. Determinant also gives a scalar. It's definitely a scalar. It's not so important that we know how to calculate a determinant, but it's for a 2 by 2 is pretty simple. You do 1 times 4 minus 2 times 3. That means minus 2. But forget about this is not so important. Yeah? What is important is that the determinant gives a sort of size of the transformation. Yeah? Assume you have the two unit vectors, 1x, 1y, and you have a matrix working on that vector. Then you're gonna see a rotation and an increase or a decrease. So I made this a bit shorter, this a bit longer, and I rotate it. So your determinant is basically the surface of that. Yeah? Typically, when a matrix works on a vector, you're gonna get a rotation and a scaling in some way. Yeah? It's rather unique if this would not happen.